Chapter 9, Part 1, Polar Coordinates. And just a friendly PSA, the Chapter 8 quiz is now pending. Due at the end of the day on Thursday, but I would advise you to tackle it before that stuff is gone from your mind, because we learn and purge nowadays, don't we? Okay, polar coordinates. So this is a different way to represent a coordinate plane. So you guys know a rectangular coordinate plane, right? Where you have so many x units, and that's right or left, depending on if it's positive or negative. And you have so many y units, and that's up or down, depending on whether it's positive or negative. Polar coordinates work very differently. With polar coordinates, you've got two values. You've got an r, which is your radius. And you've got a theta, which is your angle to the horizontal. So two values make up a polar coordinate. An r, which is the radius, and a theta, which is the angle to the horizontal. So the r tells us how many units to go outward, and each of these concentric circles represents a unit away from the origin. So 1 unit, 2 units, 3 units, 4 units. And you can make the graph larger and go bigger and bigger. So 1 unit of radius, 2 units of radius, 3 units of radius, 4 units of radius represented here. Now the angle to the horizontal works just like it did when we studied the unit circle and other things. You've got 0 degrees or 0 radians here. And this is 90 degrees or pi over 2 radians and so on. But we can go in a positive or a negative direction. Positive is counterclockwise. Negative is clockwise. And that can be confusing. It's kind of counterintuitive. But this rotation from the beginning angle and counterclockwise is positive. If you start here and you go clockwise, that's negative angular rotation. And there's no special reason for that. It's just what somebody declared one day, and we've all followed suit. Okay, so polar coordinates. Your graph should look like this. Now, I had this out to make copies for you guys so you didn't have to draw these, but the copier's down. So, sorry. I do have some tools that'll make it a little easier for you. And you can make one graph and put several plots on it. Or if you're high-tech like painting, download a picture of the interweb. So this is a set of compass and protractors. You want to make your drawing look really neat like that, you can use these. You know how to make a circle with a compass, I'm assuming. And then here I have some Sweet Tarts candy that I don't want to have. I really like sour candy. Well, I think I do, but I like that. So this is what your graph should look like. And of course, the intermediate angles, I'm assuming you just know that they're 30 degrees, 45 degrees, 60 degrees, and that's pi over 6, pi over 4, and pi over 3. And then as I go into Q2, 120 degrees, 135 degrees, 150 degrees, which is also 2 pi over 3, 3 pi over 4, 5 pi over 6, and Q3, 210, 225, 240, which is 7 pi over 6, 5 pi over 4, 4 pi over 3. And then over here in Q4, remember we had 300, 315, and 330. And it was, let's see, 5 pi over 3, 7 pi over 4, and 11 pi over 6. So you have to know all those. And you also have to know how to get there in a negative direction, okay? So if I had pi over 4, for example. So let's imagine this is 0 degrees for me. I can turn 45 degrees and face Mason. That's that. But I could also turn negative 7 pi over 4 degrees and I'm in the same place. See what I mean? So your rotation can be positive or negative to land on each of these terminal rays. Here I've written the positive values, but as in my example, if I start here and go in a negative direction, I could say that that's an equivalent radian measure. And see how I could write a negative degree and a negative angle for everything up here. I'm not going to bother with all that. That was a point of great confusion earlier, so I wanted to clear it up before we began. Okay, so know your angles. Know that the radius is the distance from the center in the number of these concentric circles. And let's plot a few points. So example 1, graphing polar points. So you've got an R, which is your radius, and a theta, which is your angle. So polar points are written like this, with the radius first, then the angle. The angle might be in degrees, might be in radians. Either one is okay. So 2 and 45. So 2 units means I'm going to come out and I'm going to be somewhere on this circle. See that? So I'm going to be somewhere on this unit, 2 units away from the center circle, because I've got 2 units of radius. And I'm going to be on the 45-degree angle. So do you see how 45 degrees is this ray, 2 units is this circle, so they meet right here, meaning that's my point. Two units in the direction of 45. So that is point A. Change the color here of B. So we'll write that one. So negative 1.5. Uh-oh. Negative radius. So what that means is we're going to go away from that angle. Do you see here we went 2 units towards that angle? Here we're going to go 1.5 units away from this angle. So this is the line that represents 2 pi over 3. This is a positive radius direction. This is a negative radius direction. So what I'm going to do is start at the center, and instead of going towards it, I'm going to go away from it 1.5 units. So instead of going towards 2 pi over 3 as we did the first time, we go away from it 1.5 units. It's a negative radius for a polar point. And the third one, which I'll change the color of again. So we've got 3 as our radius. So I know I'm going to come out here. It's going to be somewhere on this circle, 3 units from the center. Negative 30 degrees. Well, that's here. It's also 330 degrees. It's also 11 pi over 6. It's also negative pi over 6. All the ways to describe that angle. It's all the same. Negative 30. You're right here. So 1, 2, 3 units. That's point C. So I'm going to create 3 more points. I want you guys to try to plot those. So let's do D, and we'll make it negative 4, comma 5 pi over 6. We'll do E, and it'll be 3.5, comma negative pi. And then we'll do F. And we'll make that one negative 4, comma, 0. Well, no, that's too close to the previous one. Make it 3, comma, 0. So you plot D, E, and F. Here's the camera. That's the Once you finish, glance over at your neighbor if they're within visual range and make sure you guys agree. Whilst trying to maintain the distance. We're in an uptick in cases. 500 cases in our region yesterday or something like that. I think I read in the paper though that was a consequence of there was a huge backlog of tests that they processed all at once yesterday. It's all over the national news though. Huge. So if you think about positive negative angular, well, just it'd be the same in terminal R. So the location would be effectively the same. All right, so let's talk about these a little bit. Luke, where should I put this D? D is in delta.
So 5, 6, 3, go backwards.
So here?
Yeah.
Exactly right. Now, what about E? Let's see. Anna. Towards pi, yes, that's correct. Because negative pi and pi are the same angle. And then what about the last one, JT? From the origin?
Yeah.
Good job. Okay, any questions about that? All right, cool. So multiple representations. So any point on a polar graph can be represented 4 ways. So every point has 4 representations. And this is a new idea to us. Because how many ways can you represent a rectangular point? You know, if I'm on a standard coordinate plane, and I say like point 3, comma 2, how many ways can I say that? Just 3, comma 2, that's it. There's no multiple representations in the rectangular coordinate plane. However, in the polar plane, there are 4 for each point. It can be mighty confusing. So if I think about this, 4, comma pi over 4, how many ways can I say that? Well, I can say it 2 ways with a negative radius, 2 ways with a negative angle. And so it's important for me to note the corresponding negative angle. Do you see why it's 5 pi over 4? So, I mean, the corresponding 180-degree opposition angle. Because you see how if I say negative 4, comma 5 pi over 4, I land in the same place? So if I take the angle that's 180 degrees opposed to the original angle, or pi radians opposed, which is 5 pi over 4, and then I go negative r units in that direction, I land in the same spot. So it'd be sort of like this. I can take 4 steps either, or I can turn 180 degrees and take 4 steps backwards. See how I'm in the same spot? Okay, so now these angles, I can express them as positive or negative. In both cases, the angles here are positive. But another way to say pi over 4 is negative 7 pi over 4. You remember that? So instead of going positive pi over 4 units, I can go negative 7 pi over 4 units, land on the same terminal ray. In the same way that pi and negative pi are the same, because they land on the same terminal ray, pi over 4 and negative 7 pi over 4 are the same angle, because they land on the same terminal ray. As far as angular deflection is concerned, it only matters where you land or where you stop rotating. So if you stop rotating here, you're pointed at pi over 4. If you stop rotating here, you're still pointed at pi over 4. Just the means by which you got there is different. Okay, so I can say 4, comma, negative 7 pi over 4, and it means the same thing. So now we have 3 ways to say this. There's one more. You see how 5 pi over 4 could also be described as negative 3 pi over 4? So the negative angular pathway to get to that same terminal ray is negative 3 pi over 4. So I can say negative 4, comma, negative 3 pi over 4. So there's my 4 polar ways to express that point. So what if I were to say, I'm going to give you another point. So I want you to tell me the 3 other ways to express the point (3, 2 pi over 3). I'm going to give you some help with the negative signs here. I'll also give you some help with the angles. So this is angular pathways. So how do I look at this terminal method? And also subtract. Let's keep this. All right. Caleb, tell me what this first one is here.
I did negative, -3 photography.
Excellent. Then Isaac, tell me what this one is.
-4 photography.
Excellent. Mason, tell me what the last one is.
-3, -5.
Excellent. Okay, so any questions about how they got those values? To make sure, sir.
I just have a question on the one in the middle.
Mm-hmm.
I got 3.
Okay, so this rotation, so this terminal ray is what we're worried about, okay? And we can get there by rotating 2 pi over 3 in a positive direction from 0. That's the default, is the positive angle. But also, do you see I can get there in a negative pathway by going -4 pi over 3. And these add up, if you take their absolute value, they add up to be 2 pi, because that's the whole circle. So 2 pi is 6 pi over 3. So if I take 2 pi over 3 from 6 pi over 3, I get 4 pi over 3. So you can do it that manual way if the mental arithmetic eludes you. But it's -4 pi over 3 rotation to get to that same terminal rate. So this describes the same angle that this describes. You see what I mean? And this describes the same angle that this describes, which is the one that's in 180-degree opposition to our original angle. So these are 2 different ways to say the same thing. And these are 2 different ways to say the same thing. Good question. Other questions? Positive and negative angles. This, the learn and purge strategy will not suit you well in pre-calc. And I don't blame you for having it. My goodness, it's not your fault. Since like 3rd grade, you've been told by your teachers to study for this end of course test. And then after that, just don't worry about it. So the learn and purge is the default strategy of education in our modern age. But it won't serve you well in the case of advanced mathematics because everything's scaffolded. In other words, dependent upon what comes before. So if you're building a scaffold, and your 3rd layer is faulty, really doesn't matter about anything above that, does it? Because if you try to climb above that faulty layer, you're going to fall. So make sure you don't have faulty levels of learning in mathematics. Okay, so remember that r is a radius, which is the distance from the center. Theta is the angle to the horizontal. And now let's graph some polar equations. We did some points. We did some multiple ways to represent a point. Now we're going to do some polar equations where r is a function of theta. That's our polar curves, which is like C here. So what is the simplest shape of an equation in the rectangular coordinate plane? Just off the top of your head, what do you think? Easiest thing to graph in a standard XY coordinate plane.
Vertical or horizontal line.
Yeah, X equals 3 or Y equals 2. Even a skewed line, Y equals 2X plus 5. It's really easy to graph. It's innate, in a sense, to the rectangular plane, straight lines. The rectangular plane loves straight lines. The polar plane loves circles. Circles are the easiest thing to graph in the polar world. And this, r equals 2.5, is a circle. How hard is it to express a circle in the rectangular plane? Well, it's x squared plus y squared equals r squared. Or if you have a center other than the origin, x minus h quantity squared plus y minus k quantity squared equals r squared. In other words, it's a pretty complex expression. But here, look how simple it is in polar. R equals 2.5. This is the beauty of polar. It can do circles really easily. So we go 2.5 units from the center at all angles. And then you just connect those with a line like so. And I should have done that in red. Let me fix that. So the red is a circle, 2.5 units. And guess what? Your calculator can do this. So with me, go to your calculator, hit mode. First of all, make sure you're in radian mode because you'll need to be. We're going to use radian later on. And then go down to where it says func, par, pol, seq. Now we use func all year, function, right? We used parametric in chapter 7, that last section. You remember that? The graphs that had a direction in addition to an XY value. And now we're going to use polar. So hit enter, and then y equals. And look what you got. You got r's here. So we'll punch in r equals 2.5, and we'll zoom 6 for the standard window. Now notice that it is not circular, or doesn't appear to be. It's because your screen is skewed. So you guys know how this works, right? If you have a picture of a circle and you pinch it downwards, do you see how it would become an ellipse? So that's what we've done here. We've pinched it downwards because we've got more X screen, more pixels in the X direction than we do in the Y. But we can control for that. So if I change it to go from -4 to 4 on the X and -3 to 3 on the Y, now it's a circle. So that's what it means when it shows you the other. It is a circle. Okay, so let's do some more. B, theta equals pi over 8. So theta equals, what am I doing? Look at that. Purple. So theta equals in polar equations is a straight line. So r equals something is a circle. Theta equals something where it's a constant value is a line. So pi over 8, that's less than pi over 6. You guys agree? So it's going to be somewhere in here. So let's just say this is pi over 8. And this can be 180 degrees opposed to pi over 8. So our line is going to be that. So that is our straight line in polar. Your calculator won't do that. TI calculator. If you want a Desmos or Wolfram or something like that, it will. But TI calculators don't like lines in polar because you can't set theta equals something. It has to be r. R is your only dependent variable. Yeah, so if I go, you see how I can't set theta equal to anything here. It's not an option. But theta equals pi over 8 is this line, straight line. Now, a function of theta, a curve. So we had a circle. We had a line. And now this last one in green is a curve. And in order to plot that, I'm going to erase what we had here before. Because this one's a little more complicated. And we'll need a little chart. So let's do theta and r, and we'll pick a few values here that'll help us kind of understand the pattern. So I'll pick 0, and 2 times 0 is 0. I'll pick pi over 4. Pi over 4 times 2 is pi over 2. So I'm just plugging theta into this expression to get off. The same way you would do with y and x. And then I'll go pi over 2 times 2 is pi. So let's plot these points and see if we can see a pattern. 0, 0. And then if I go pi over 4, I go out pi over 2, which is 1.57. And then if I go to pi over 2, which is 90 degrees, I go pi units, which is 1, 2, 3, and then a little more. So you see how we're doing this spiral business? So this is a spiral. And it's got a special name, these types of spirals. They're called the spiral of Archimedes. The spiral of Archimedes. So it looks cooler on your calculator, and it's a lot easier to do. So let's make a more involved graph of this on our calculator. So 2 theta, and I want to change my window. So theta min, theta max, how many degrees do you want to go, or radians in this case? 0 to 2 pi. I'll tell you what, let's go 0 to 5 or 6 pi. So 3 complete times around. The theta step, the default is good. Now I have to think about, do you see how the radius is going to be double the angles because r equals 2 theta? So this is 18. I'll need this to be about 40 units in each direction. And I'll just go 30 units in each direction here. It'll cut off a bit of it, but you'll get the idea. Oh, well, the x-max is -2. Did I do that in both cases? Wow, I'm really losing it. So here we see the spiral of Archimedes. Yes, get the idea here?
Does it always rotate counterclockwise?
Yes. Unless you were to, there's a way to make it not do that, but it's pretty complicated. Because that's the positive rotation. You would have to go yeah, if I went negative, it would work. Let me show you. -2.
Negative is the same.
That's,
Rotates the same.
yeah, but it's the opposite side of the y-axis. Pretty neat, though. Yeah, to make it rotate the other way, I'm not sure. I'll have to think about that. That's a good question. Other questions? So I taught you how to do a circle, a line, and curve in polar world. That, ladies and gentlemen, is chapter 9, part 2. So your task is to do page 538, numbers 2 through 26 even. 2 days in a row, I got done pretty early. You're welcome. You come into pre-calculus expecting to work for an hour and 10 minutes, don't you? No. You can say a lot of things.